Today we will be discussing the half adder and the full adder. However, before I get to that, I need to discuss binary addition. So, binary addition is very similar to decimal addition with a few key differences. So, let's set up a problem 0, 1, 1, 0, and 1, 0, 1, 0, or 6 and 10. So, binary addition, you go top to bottom just like in regular, and you will add up. However, if you have two ones, you will carry. So 0, two ones will become a 0 with a carry. That's again two ones and a carry, and two ones and a carry. So you get 16 because 10 plus 6 is 16. So when you notice this, you can see that a 0 and a 0 will produce a 0, and a 1 and a 1 will also produce a 0, but will produce a carry. 0, 1, 1, 1, and 1, 0, 1, 0. So in this case, it's 1. And then this is 0, carry the 1, 0, carry the 1, 0, carry the 1. So in this, you can see even more clearly that the adding part is an XOR operation, but the carry is an AND operation. So you only carry if you have two bits. But what if there's three ones? Let's do 1, 1, 1, 1, and 1, 0, 1, 0. Again, this is 1, this is 0, carry the 1, this is 0, carry the 1. When you have three ones, you will put a 1 and carry a 1. So this is harder to do because you cannot do it with just an XOR and an AND operation. You have to do it with multiple half adders, which we will see later. So let's look at the truth table. A half adder simply adds the two bits and produces the sum and carry bits. So 0, 0 will produce, of course, 0 and 0. 0, 1 will produce a sum of 1 and a carry of 0, and as will 1 and 0. But 1 and 1 will produce a sum of 0 and a carry of 1. The limitation of this is that you cannot take into account a carry in bit. That's where the full adder comes in. The full adder allows us to take into account a carry in bit. So this overcomes the limitation of the half adder, in which you cannot take into account a third bit, and it allows you to chain multiple adders. So up until this point down here, the truth table is the same because there's no carry in bit. And when there is only two, it acts as a half adder, producing the same output. However, when all three inputs are 1, the full adder will output a sum of 1 and a carry of 1. This is critical because you need to be able to carry in order to chain, and carry out in order to chain adders. So this diagram is a diagram of the half adder. It's made of an XOR gate and an AND gate. Again, the XOR gate takes care of the sum, and the AND gate takes care of the carry. So XOR, if there is only one input, the sum will be 1. This fits our truth table. Back here, a single input will produce a sum of 1, but as an XOR, two inputs of 1 will produce a sum of 0. The AND gate takes care of the carry, and in the case of two inputs of 1, the sum will be 0 and the carry will be 1, just as we expect. Now that is one of the common ways to make a half adder. In the case of our circuit today, I did not have a XOR IC available, so I use an OR inverter and AND, which is functionally equivalent to an XOR gate. So this would produce the same output. Let's go through it just to check. If A and B are 0, obviously, the sum will be 0 and the carry will be 0. Because the AND gate will produce 0, the OR gate will produce 0, and if the OR gate produces 0, the AND gate right here will produce 0. A is 1, or B is 1. The OR gate will produce 1. The AND gate will produce 0. This inverter will change that to a 1. So it will be 1, 1 to create a sum of 1. And the AND gate will be 0 and create a carry of 0. And when both are 1, of course, the AND gate will be 1. The inverter will change that to a 0. This AND gate will therefore be 0. And the sum will be 0, but the AND gate will be a 1 and the carry will be a 1. So that is the half adder that we will implement later today. This is the full adder. So as you can see, the full adder consists of 2 half adders and an OR gate. And the carry out and sum, and the A, B inputs, and the carry input. So it will take a while, but let's go through the different variations of inputs and see if our truth table holds correct. Right here. So 0, 0, 0 will obviously output 0 here, 0 here, and 0 here and 0 here will produce 0 and 0. So everything will be 0. 1, 0 or 0, 1 will produce a sum of 1 and a carry of 0. So a 1 here and a 0 here will produce a sum of 1 and a carry of 0. So there will be a 0 carry and a 1 sum. 1, 0, 1 or 0, 1, 0 will produce, again, a sum of 1 here. However, the input here will also be 1, so the sum will be 0. The carry will be 1. So 1 or 0, the carry will be 1. And the sum will be 0. And finally, 1, 1, 1. So remember that the sum is an XOR operation. So 1, 1 will produce a 0, but this is a 1. So the sum will be 0 and 1, so the sum will be 1. The carry will be 0. However, because it's a 1, 1 here, the carry will be 1, and a 1 and a 0 will produce a 1. So a 1, 1, 1 will produce 1 and 1. Hello YouTube, this is a demonstration of the half adder discussed previously in this video, which I have placed here for reference. So as you remember, a half adder consists of an XOR gate and an AND gate sharing inputs, where the XOR gate outputs the sum and the AND gate outputs the carry. However, because we did not have any XOR ICs to work with, I decided to implement this half adder on the right, which uses an OR, not an AND gate, instead of an XOR gate. So as you can see on this breadboard, input A is on switch 3 right here. Input B is on switch 8. The sum light is represented by the LED on top, and the carry light is represented by the LED on the bottom. So if any one of the inputs is 1, then I should have a sum of 1 and a carry of 0. If they are both 1, I should have a sum of 0 and a carry of 1. So let's check it out. When I press 3 down, which is A, I get a sum of 1. When I press B down, which is switch 8, I get a carry of 1, and a sum of 0 and a carry of 1. When I turn 1 off, it goes back to a sum of 1 and a carry of 0, and 0, 0 produces 0 and 0. This is a demonstration of the full adder discussed previously in this video, which I have placed right here for reference. This circuit is basically 2 half adders and an OR gate. The top one is the half adder I used earlier with some modifications. I added cables from the outputs to the inputs of this half adder, and I added a carry input bit to this OR IC right here, the 7432 chip. So these lights represents the sum and the carry. This will represent one half adder. This will represent the full adder. So like the single half adder, when I put a single, the sum is 1. When I put both, the carry is 1 and the sum is 0, just as in the half adder. However, when I turn on the carry in bit, you can see that the sum is 1 as well. So 3 bits of 1 will cause a 1 and a carry. That is all for today, and I hope to see you next time for the ripple carry, where we will apply the full adder to add multiple bits.